And it's not by accident they stuck the 5 all the way down over here to be a mirror of the 2, and that comes from them both connecting to the 1 where they connect. It's not an accident.
Oh. And then the 8, the third part there, is the 2 small things filled
overlap.
in.
They are reciprocals, they always make 1, and it has a use. Everything we're seeing here has a use. And the use is this. Okay? The use is 1 times 1 is 1. 2 times 5 is 10, which equals 1. So I go away from 1, 1, 2, which is a 4, and backwards, 1, 2, which is a 7. And 4 times 7 is 28, which is 10, which is a 1. Do you follow that?
Do it again.
No,
Okay.
it's too fast.
I have to just see. It's weird because I'm going very long this way and very short
But you're
this way.
going to adjacent nodes from the center.
Exactly, from the 1. I'm using the 1. I'm not on the 9 right now, I'm on the 1. We learned about polar relationships, which is by the 9. But now we're going to learn reciprocal relationships. The polar is different from the reciprocal. The reason I have the answer to everything is because I'm combining every principle that exists into one ball of yarn. So right now we're going to work not on the polar aspect, but we're going to work on the reciprocal. Reciprocals always equal their beginning point. Okay? 1's the beginning, so 2 and 5 is the next distance. And 2 times 5 is 10 equals 1. Okay, and so now I'm going to go 1, 2, which is the 4, two lines away. Bear in mind that every one of these lines, the ratio of this line to this line to this line is your golden, it's all your means you could ever, everything you want to know.
But you're starting with 2 and you're looking at 1 and 4 in relationship to...
No, I'm not going to do that yet.
Oh.
I'm only counting, I'm going to start with 1, I must end up on 1.
Oh.
And this must be a 1, 2, because if this is a 1, I want 1 times 1 is 1. Watch. I'm going to just do it.
Okay.
1 times 1 equals 1, because this is really 1 over 1.
Right.
Okay. So I go over here, and because I have 2 parts now, I don't have to multiply 2 times 2, and, well, 2 times 2 is 4, I've never done this before. 2 times 2 is 4, and 5 times 5 is 7, and 4 times 7 is 28, is 10 is 1. Yeah, it still worked anyway. Okay, it's okay, I just thought, I like to do new things when I can find new things to do, because, okay. So 4 times 7, which is now 2 away from 1, 1, 2, 1, 2 equals 28, which is 10, which is 1. And then I go 1, 2, 3, I end up here this way, and I go backwards, 1, 2, 3 this way, so I go 8 times 8 is 64, is 10 is 1.
Yeah.
Always equals 1. And I found that this shape always makes the demarcation line. It's called a shear, it's called a, it's real important for modeling electricity. But I won't go on to it further on the chart because you'll see it elsewhere. But since Charlie brought up one other thing, let's do with 2 now. 2 times 2 is 4. Okay, so I go this way. 1 times 4 is 4. Then I got to go like this. 8 times 5 is 40, which is 4. And 7 times 7 is 49, which is 4.
Yeah.
It's always going to be a shear, consistent.
And one you're moving backwards, 1, or forward 1, and then the next time you're moving backwards 2,
right.
Forward 2.
Now 4 times 4 is 16, which is 7. So I go this way and I go, what is it? 2 times 8 is 16, which is 7. And then 1 times 7 is 7. And 5 times 5 is 25, which is 7.
Is that fractal though? That's fractal.
This whole thing's a fractal. I have a chart in here that not only, that I don't have to say one word, that is so beautiful, what's actually behind this board.
This whole thing, doesn't it also have its own mirror image behind it?
Yeah, but
it has an
I'm listening to, there is no but. Yes, it has a mirror image, but there's certain laws, there's certain rules, we just have to understand what those are. What is that mirror? What's its polarity? What's its number? What's its location? Based on up, down, right, and left, front and back. Here we go. 1, 2, 4, 8, 16. This is a very primitive chart. The binary code is a 6-number digit repeating pattern in the decimal system 124875. This is considered the binary code. This is computer switching. I call it on and off. But I've already said 0 is not the member of any multiplication series. Okay? 0 and 1 cannot be the computers of the future. It just doesn't work. That's why they're so slow and obsolete. Okay? And this toroid system is the supercomputer. But I'm just showing one point, which is the score. content versus quality. Is we have one point here. What is its content? 1. So there's your quality to the right and content to the left. Got it? Now we have 2 points here. What's their content? 2. Does everyone understand that? No. What's their quantity? 2. Okay. And what's their content? A 5. Now we have, that's what a reciprocal is.
I'm not paying attention really very well.
Okay. Now we have 4. 1, 2, 3, 4. And what's their content? 0.25, which equals a 7.
Oh, okay, right.
Oh, I see.
Wait a minute.
Okay.
See, 2 has 7, 5.5 make 5.
It's not 0.5, 0.5, because we're only looking at each one. There's 4, one of these.
Right.
Okay? And each one of those 4 represent 0.125. No, they represent 0.25 if you're looking at the top.
So it's
1,
like
2,
a
3,
pyramid.
4.
Maybe it's meant to sell us something?
It is a pyramid. It is. I'm showing you that the binary system is a pyramid, but it's a pyramid that is not binary.
So on the right is
If anything, it's...
on the right is the branch number, and on the left is the value of.
Oh, right. I showed the vortex in, out, last but least point, which is not going to be... I showed the 2 and 5 is not accident. As long as we're on these charts. I'm showing the vortex action. I'm showing how it moves in a vortex. Showing infinity. It's just a cosmic grinder. Okay. I'm showing the music scale. Classic musical scale is the doubling circuits too. From C to C to C is 1, 128, which is 11, which is 2, 256, 13, 4, 5, 12 is 8. It's the same thing. Your doubling circuits. I said the ancients did know this, and that pretty much sums that up right there. Okay. 5, 1, 2. 128 is 11, 2, 256, 13, 4, 5, 12, 8, 1024, 7. Remember, 7 always comes after the 8, not before. 1, 2, 4, 8, 7, 5. Okay.
No, there is, because I've worked with it in group theory textbooks.
But there's nobody that
I've never seen it done like this before.
There's no... That's right. This is a different kind of
This
process.
is really, really rich territory for mathematics, at least. That's what I'm seeing.
So the whole
It's a whole new
Yeah, it's very
frontier.
rich. But, I just don't know whether if you got a real good number theorist from some university would say, oh, that's just, I did that last year or something like that.
I've never...
met anybody that...
There ain't a teacher around who's ever seen this before that can explain it.